Guys, last time we were talking about electron configuration notation. We said that we have three methods, and the one that I explained is this one, electron configuration notation, or what we know as full notation. Now the second method, today's method, is orbital notation. So remember when I told you that an orbital represents the spin of an electron, and it's represented by two arrows. Okay, this time we were going to implement this method to represent or to show the electron configuration of any element. Now we're going to start with an example, selenium. Selenium, if you take a look in your periodic table, you'll notice that the atomic number is 34, and this is the atomic symbol. That means that we need 34 electrons. So we're going to make use of the tree that I gave you the other day in order to complete the full electron configuration notation. So we always start by this point right there, and we say 1s2, 2s2, 2p6, 3s2. We follow, and it continues to 3p6, then 4s2, then 3d10. At this moment I know I have 30, so I need 4 more. So after 3d I have 4p, but instead of using 6 I need just 4. Now to make sure that I did it correctly, I will count. Okay, so I have 2, 2, 2, and 2 makes 8, plus 6, 6, and 4 makes 16, plus 10, and let's say 8 and 16 is 24, plus 10, 34, so it's okay. This is the full electron configuration notation. But I said today we're going to learn about orbital notation. So guess what? To represent or to show orbital notation, you will need the electron configuration notation. So this is what we know as the first step of the solution. The second step is to show the spins. For example, 1s2 is represented by a box, and this box can hold 2 electrons. Okay, like I did over there. So this is what we're gonna do. We're going to replace all of them, and we're gonna say in the first period I have 1s2. Okay, this is the equivalence. In the second period I have 2s2, which is another box, but also I have 2p6. There you go. In the third period I have 3s2, 3p6, and 3d10. So I have 3s2, 3p6, and 3d10. If you count, I have 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. P6, 1, 2, 3, 4, 5, 6. S2, 1, 2. There you go. Now in the fourth period I have 4s2 and 4p6. 4. So for the S2, I know it's full. Okay, and now following Hund's rule, I need 6 electrons. So how do I do it? Easily. Okay, now from 4p4, what we have is just 4 electrons, so I need just 4 arrows. How am I going to start filling it? Easily. So we start in each box, every arrow upward. Three. Now, I don't need 3, I need 4. So the next arrow, you come to the first box, and now you do it downward. And there you go. That is the orbital notation for selenium. Now let's do another example. We have rhodium 45. So this is the atomic symbol, and this is the atomic number that I took from the periodic table. I won't show you my periodic table, but here you go. Okay, so the first step, as we said before, is to build the electron configuration notation, as usual. So we say electron configuration notation of rhodium. Take this and we follow the pattern, and we have 1 S2, 2 S2, 2 P6, 3 S2, 3 P6, 4 S2, 3D10. I know in 3D10 that I have 30, so I need to keep going. I need 15 more. So 4 P6, I need 9 more, so I continue. 5S2, and I need 7. So I go to 4D, but instead of 10, I just need 7. Now to make sure that I did it correctly, I will add them individually. 2, 2, 2, 2, and 2. It's I have 10 plus 6, 6, 6 is 18 plus 10 and 7, that makes 17. 10 plus 35 is 45, so we are cool, we did it right. Now to build the orbital notation, we're just going to replace by using boxes. So you know, if I have S2, I will use a single box. If I have P6, I will use this box like that. If I have S2, P6, oopsie, never mind, we continue. I have S2 again right here. I have P6 full right here, but I have 3D10 over there. I need 10 boxes in the third period, and in 4D7. Okay, let me see. In 4D7 I have orbital D, which I'm gonna draw the 5 boxes to hold 10 electrons, but I won't draw 10. I will draw just 7. So first of all, I need to draw upward electrons. So 1, 2, 3, 4, 5. Now I continue 6 and 7. And last one, but not least important, is 5s2. So there you go. This is the orbital configuration of rhodium. Okay, we continue and we have a more challenging problem, that is element mercury. Atomic symbol is Hg, as we have in the periodic table right here. Pam, pam. And the atomic number 80, that represents that we need 80 electrons. So, first step is to build the electron configuration notation. So we need 80 electrons. So this process is a little bit longer. It's gonna take a while, but we have the time. One S2. I follow this, okay? 2s2, 2p6, 3s2, 3p6. Okay, sorry about that. Empresa Energía Honduras doing what they do. Okay, after 3p6 it continues in 4s2, then it follows to 3d10, and then it continues with 4p6. I know that I have 30 here, so I'm going to 36. Then it continues with 5s2, 38, 4d10, 48, 5p6, 54, 6s2, 56, and then it comes 4f14, that makes 70, and after that it comes 5d10, that makes 80, okay? The entire area, 80, okay? Now there you go. So I will line up this. Okay, so first I draw the individual boxes for the s orbital that keeps 2 electrons, 1 and 2. So as I have 6 periods, I need 6 boxes, 1, 2, 3, 4, 5, 6. Now I need 3 boxes of 2 electrons, here, 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 so 4 boxes. 1, 2. Sorry, I did terrible calculations before this. Okay, there you go. 4p6, 3p6, 4p6, 5p6. Okay, now I need the 310, the 410, and the 510. And remember, I have one here that was 14, so I'm gonna draw it here. Okay, sorry guys, it didn't fit, but at the end I kind of did something, so I'm holding my cell phone As you can see here, now I completed it. Everything is full, even this one. It is 4F14, so I need 7 boxes of 2 electrons. 1, 2, 3, 4, 5, 6, 7 times 2, 14. So this will be the full configuration of Mercury. Take a look. So remember, first step, electron configuration notation full, and then replace everything by boxes and arrows, because those boxes represent orbitals, and remember, each orbital can hold 2 electrons or 2 spin states.